Hey, 1332, Jacob here. Last week I spent most of Thursday grading heaps of exams. But what is a heap? Let's talk about it. Welcome to Recitation, guys. I'm not doing that intro again, so hopefully you guys enjoyed it. You guys saw all the stuff I put in the announcement, lots of things. I'm putting the name of the songs in that little intro thing. You guys have the song list form that I think you guys should be able to see the responses on. I'm making the playlist of the music I'm actually using. So lots of changes based on your feedback. I'll try to keep doing stuff based on that as people like it. But regardless, let's get started. We got heaps to talk about today. Get that set up. Alright. And your usual announcements. Homework 5, that's your current homework on heaps and priority queues. That's going to be due this Friday. It's not that difficult of a homework. It's really only 2 helper methods and then using them properly. I will mention something, just because it was recently due. Homework 4, the BST homework, if you had difficulties with that, don't worry. That is probably one of the hardest homeworks in this class. Definitely in the top 3 most difficult homeworks in this class. So if you had some struggles with it, don't worry. It's not like the homeworks get harder from here for everything. That's one of the hardest. Homework 5 is a little bit on the easier side in comparison. After that, though, we're going to release homework 6 this Friday. That's your HashMap homework on a linear probing HashMap. That is another one of the harder homeworks in this semester. Unfortunately, the hardest homeworks are a little close together. I would say homeworks 4, 6, and 7 are the 3 hardest. Although, if you do well on homework 4, it makes homework 7 very easy. So it's kind of a little bit of a rough point in the semester, but once you get through that, the rest of the class can be a little bit easier in terms of the homework. But either way, that's going to release this Friday, and it's due next Friday on October 2nd. Exam grades. You took your exam last week on Wednesday. Things mostly went well with that. There were obviously some issues with scratch paper a lot of people had, a couple other things on the exam that we tried to fix. Hopefully we'll have those sorted out better for exam 2, but overall it went pretty well. We graded all of the campus section exams on Thursday, and we graded all of the online section exams on Friday, so all of the actual hard work grading is done. There's just a couple last minute things we'll need to do. Our goal is to get those grades back to you sometime on Wednesday. Once we release the grades, there's going to be a brief 1-day freeze period for regrades, so you won't be able to submit a regrade the same day we give, or within a day of us giving the grades back. That's just some time for you to look at your exam and actually consider how your exam was graded and if you actually have a valid regrade request or not before you come to the TAs. This week's recitation worksheet is on Canvas, and for today we're going to talk about some heap operations since we only covered the intro of heaps last week, including BuildHeap, which deserves a category to itself, and we'll do a very brief intro of maps and HashMaps. So with that, let's get started. These first 2 pages are exact ones I had last week, so I'm not going to spend a lot of time on them, just a brief bit of a refresher. I don't expect people to write all this down again, because we had it last week. Heaps are these data structures that we use to keep track of either the largest thing in a set of data or the smallest thing in a set of data. Remember, we can think about them as complete binary trees, that's every level being filled through the last, and we have this order property where all the parents are always larger than the children or smaller than the children, depending on the type of heap we have. So in a min heap, our smallest data is at the top, and with a max heap, our largest data is at the top. When we do our modification operations, the first thing we're going to do is fix that complete shape property, make sure we maintain it, and then we'll go back and fix the order property later, because that's the harder one. Remember, our implementation of these heaps is with arrays. We don't actually use nodes like we did with the BST. Since we're using a complete tree, we can use an array that has no gaps in it, which is really convenient. The one thing we're going to have is this first spot of the array, index 0, we're just going to leave that blank. We're never going to put data in there. The reason we do that is because it makes these calculations super easy. We can get a parent index by dividing by 2, we can get a left child by multiplying by 2, and we can get a right child by multiplying by 2 and then adding 1. So that's your really fast refresher on how heaps work. Let's talk about how some operations on heaps actually function. So this is going to be the new stuff. Adding is usually a good first thing to talk about, so let's start there. When we add an element to the heap, the first thing we need to do is maintain our shape property. That's the much harder one to fix later. So, our array is contiguous. That's kind of the whole reason these complete trees work. So in order to keep that, the only place we can add our data is at the very end of the last level, which is the very end of the array. And the index that's going to be at is at index size plus 1. Now you might think this looks a little weird, because like with array lists and stuff, the last spot that you added to was index size. And remember, because it's a heap, we have that blank spot at index 0, so everything's kind of shifted to the right by 1. So our spot at the back of the array is going to be size plus 1 instead of size. This off by 1 is going to be important when you're checking your resize conditions too, so don't forget that. So after we've put the data at the end, now we need to fix the order property. And we're going to do that with an operation called heapify up, or upheap. I'm going to generally call it upheap, but these are the same things. You might see it differently in different places. How the upheap operation works is we take some node, or piece of data, we compare it with its parent, and then if those two nodes are out of order, so either the parent is greater than the child in a min heap, or the parent is less than the child in a max heap, then we're going to swap the two. And then we keep repeating this, moving up the tree up the heap at every single iteration until we either hit the root and we no longer have a parent to compare with, or we don't do a swap. As soon as we do this comparison and find that we don't need to do a swap, we're allowed to stop our upheap immediately. We don't need to keep going. Now, a decent way to see this is with some examples. So let's start with nothing and add some things to our heap and see what we get. So the first thing I'm going to add is I'm going to add 5. So in my backing array, size is 0 right now, so I add at index 0 plus 1. And that represents a heap with just 5 in it. So adding to an empty heap is obviously really easy. Now let's add something else. Let's add 10. So again, adding an element, index size plus 1 is 2 here. Now that's fixing my shape property. Now I need to fix my order property. 10's at index 2. So to compare with its parent, that's 2 divided by 2. So index 1. I can draw this out. So this is the intermediate of our heap. So I compare 10 with its parent, which is 5 at index 1. I see these are out of order, because this is going to be a max heap. So I'm going to swap the two to get 10 and then 5. So now I would look again, but 10 is obviously at the root, so there's no more swaps I can possibly do. Now for the next thing to add, let's go ahead and add 60. So you see that 60 kind of goes on the rightmost side of this bottom level and the next spot in our array. Now I do my comparisons. The parent of 60 should be 10. We can see that in our index calculation. 3 divided by 2 that would be 1.5, but in integer division that gets just cut off at 1. So I compare these two. They're out of order, so I'm going to swap them. And when you're going between the tree representation and the array representation, an easy way to go from array to tree is, or an easy way to go back and forth is it's basically just like a level order traversal. Like going from here to here is just 60, then 5, then 10, then all the stuff on this level, and vice versa. You can think of this as the root, then the next level left to right, then the next level, etc. So it's not that hard to go back and forth between these two. So early on, I'll be drawing out both. Later on, I'll only use the array representation when we talk about BuildHeap. So the next thing to add is going to be 50. We're done with this level, so we have to make a new level down here. And when we add 50, we compare it with the data above it. So that's the 5. You can see it's at index 4, and 4 divided by 2 is 2. So I compare these two, and I see they're out of order. So I swap them. Make sure I'm not going off the screen. I was close. So now I have 60, 50, 5. That's a little off the screen. 10, So that's what our heap looks like. But now I've swapped up 50 to index 2. Index 2 still has a parent, so I need to compare 50 to its parent of 60. In this case, there's no out of order, so I'm allowed to stop because I did a comparison and there wasn't a swap. I'll give you guys a couple more seconds to write everything down or take a picture before we go on to the next page. Or before I start doing the next operation, which is going to take me to the next page. Okay, so for the next operation, we're going to add 1. Oh, this is actually... I have a lot more space than I'm probably going to need, I think. I can make it work. So adding 1, we compare it to 50, which is its parent, 5 divided by 2. We see that there's no out of order, so we don't need to do any swap. So now I'm going to copy that heap onto my next page, and we'll do one last add operation. So 60, 50, 5, 1, 10. I apologize for not saying it in the same order that it goes in the array. That's just how I'm writing it. So the next thing we're going to add is we're going to add 40. So when we add 40, we can see that it's going to go right here in this spot. So I can redraw just so you can more clearly see what's going on in this operation. And this is the array associated with it, 60, 50, 10, 5, 1, 40. Now I do my comparison. 6 divided by 2 is 3, so I compare indices 6 and 3. I see that these are out of order. So I'm going to swap them. And I'm left with now 40 here and 10 here. Nothing over here on the left side of the tree changed. So these are a couple add operations. Ooh, that tilted my camera a lot. These are a couple of add operations. Hopefully it makes sense. If you got a couple more of these, you could probably do some of them. It's just put that in the last spot and then repeatedly compare against the parent. See if you need to do a swap. So here, after we do this swap, we compare again. We'd compare 40 to its parent of 60, because that's the parent of 3. And we'd see that there's no swap, and then we're allowed to stop. So you just keep repeating this process until you don't get a swap or you reach the root. So adding is a relatively simple process. We covered some code for it in lecture for people in the lecture section if you want to take a look at that, but it is only a few lines to do these comparisons. It's not that bad. Removing is what ends up being a little trickier. So I think everyone's had enough time to probably write this down or take a picture. We're going to move on to removing next, which can be a little trickier even though the process is pretty similar. All right, now let's talk about removing from a heap. So when we talk about removing or accessing anything from a heap, the only thing we actually really care about is the root, the index 1 of the heap. We only care about looking at the root. We only care about removing from the root. We never care about removing at some random other index of the heap. And that's just the same reason that we only ever remove from like the top of a stack. It's just not important to us to care about other pieces of data in there. We're using a heap because we want that data at the root. So same thing, high-level overview of the steps. The first thing we do is we have to save the data that's at index 1. That way we can return it to our user. Same thing you would do in a linked list before you start manipulating the nodes. You can set like your dummy, your temporary variable to it. Same thing we use the dummy data for, or the dummy node for, sorry, in BSTs. We just need to store that data. Then our next step is we copy the data from index size. Remember, that's the last non-null thing in our heap, to index 1, which is where the thing we're trying to remove was. Then we're going to null out index size. That's essentially just taking the element from the bottom of the tree, the last element, and just moving it up to the root. Then the operation we're going to do is called heapify down, or down heap. Notice this is a different operation than what we did for add. You should have if you write a helper method for it, which I recommend you write a helper method for down heap. You don't have to write one for up heap. I recommend you write one for down heap. I'll explain why later. But this is a different method, and we're going to perform this down heap operation at index 1. I specify at index 1 for a reason here. Again, I'll cover that later. How this down heap operation works is we take some node, compare it to its children. So if it might only have one child, or it might have two children. We have to account for both cases. Then after we compare with its children, we look to see if the order property is violated. If the order property is violated, then we're going to need to do a swap, just like we did with up heap. But we need to have a little different logic here. In a min heap, if the order property is violated, we want to swap with the smaller of the two children. So even if both of the children violate the order property, we pick the smaller one to swap with. In a max heap, we're going to swap with the larger child, for kind of the same reason. And you can imagine that if we pick the larger child in a min heap to swap with, well, now the order property is still violated between the child we did pick and the smaller child we didn't pick. So this makes a lot of sense. And I know in this explanation I wrote that you check if order property is violated and then this logic, but a lot of people in their code find it's easier to figure out the smaller child first and then check if the order property is violated, or with the max heap, find the larger child first. So whichever you do is up to you, but the second one, the one I just mentioned about figuring out which child first, that tends to be cleaner code. So I recommend that one. And then just like with upheap, we're going to repeat this process until we reach a leaf or we don't make a swap. And again, when I say repeat this process, I mean whichever child we swap with, that's the child that we're going to try to downheap on next. So we start at the top of the tree and we keep going down the tree with this operation until we don't make a swap or reach a leaf node. And you can kind of think of this as like bubbling down that data to the correct spot where it's supposed to be at. So I'll give you guys a couple more seconds to write stuff down or take a picture, and then we'll move on to an example. Okay. I think most people will have gotten it by now, or you can just pause and get it before we move on to the next spot. Let's go ahead and do an example. So this is going to be our tree. You'll notice it's the same heap that we ended with after all the add operations. So if you have that and want to just operate on it next, you can. But otherwise, you can always redraw it. Now again, I don't need to specify what we're removing with a heap operation. When I say remove, we always know that we're talking about removing the root. So the first step is going to be, we have our data index 1. We're going to copy the data from the end of the array into index 1 and then null out this spot. So notice, unlike all the swap arrows that were double-sided, this is a one-sided arrow. We're just moving the 10 down. So that's going to result in something that looks like this. So you see we've taken 10 and we've moved it up into the root. So obviously our shape property is still good because we only chopped off this end piece and that doesn't affect our shape. But now the order property is messed up. Let's go ahead and write this down. So, how do we do order property? Well, we've got our two children, we've got 50 and 40. We want to look at which one of the two children is larger, because we're dealing with a max heap. In this case, 50 is larger. So then we would compare 50 to our root, because remember we can get our two children by doing our index times 2, and our index times 2 plus 1. That's how we find our two children. So 50 is our larger child. It's also larger than the root, so we can swap them. We end up with 50, 10, 40, 5, and 1. Then now, we did a swap, so we have to continue on with our down heap operation. We now look at index 2. Its two children are at indices 4 and indices 5. We can compare, see that index 4 has the bigger child, which is 5. Then we compare 5 to 10. We see that the order property is not violated here because 10 is bigger than 5, and we're dealing in a max heap. So we don't need to do a swap, and we're completely done with our down heap operation, and thus we are done with the remove operation. You can see we still have a complete tree, and the order property is still maintained. So you can see that these operations, especially on diagramming, are pretty straightforward to do. Writing the code to account for some of like the weird edge cases of when you don't have children or when you only have one child, those can be a little bit tricky, but that's kind of the only real challenge in this homework, so hopefully it's not too bad. I'm giving people time to write this down. Then the next thing we're going to talk about is we'll take a brief pause to talk about the efficiencies of these operations, and then we'll start talking about BuildHeap. Yeah, so someone asked a good question. The next down heap you do after you do a swap is based on whichever child you swap with. So we don't do anything with 40 over here because we swapped with the 50. This is the index we're going to do our next down heap on. So if you make it a helper method that takes in an index as a parameter, you can see that it's really easy to do as a recursive helper method, which is what a lot of people choose to do. It's not required, but a lot of people choose to do it like that because you can just make a recursive call on whatever child you swap with. All right, but let's do a brief pause and talk about efficiencies. So with heaps, the only efficiencies we really talk about in this class are worst case efficiencies. There's some weird math involved when you start talking about average case efficiencies, and again, best case doesn't really have a lot of meaning with data structures, which I've talked about before. So we're only really going to talk about worst case. So with heaps, with our add operation, remember we just put the data in that last spot and potentially bubble it up to the top. Now with heaps, we're dealing with trees that are always complete. Remember, complete means things are always balanced. So that one branch up to the top is only ever going to be O of log n length. Now, this is an add operation with an array, so I have to specify that this is an amortized operation. We might have to resize the array. And for heaps, when you're resizing, you just copy everything to the new array, then do the add operation same as normal. Don't worry about trying to do the up heaps while you're copying. We don't require that on this homework. It's not very important. Just do the copy, then the up heaps. It's a lot simpler that way. Likewise, remove. We copy the thing up to the root, which is O of 1 time, and then we might have to bubble it all the way down to 1 leaf through the down heap operation. So just like add, that's going to be O of log n. And I can mention that this is because these operations are O of log n. I don't specify the amortize here for the up heap because that's separate from the add operation. Add is what might have to do the resize, because these only really have to go on one branch of the tree. Access, again, only thing we ever care about accessing in a heap is the root. That's the data at index 1, and because we have an array, we can access index 1 very fast. This is going to be O of 1 access. Now, let's talk about one last heap operation in BuildHeap. With BuildHeap, our goal is that we're starting with some array of data in any order. It can be in heap order, it can be in opposite heap order, it can be sorted, it can be reverse sorted, it can be whatever you want. Starting with some array, we want to turn it into a heap. Now there's two ways we can do this. You can do it the same way you did in your BSc homework with that collection constructor. You just call add on every single element. Add takes O of log n time, and we have n elements, so this would take O of n log n time. And that's really slow. You can see that n log n for what we're calling a single operation would be one of the slowest things we've talked about in this class so far. So maybe there's a way to avoid this, and it turns out there is. And this is what we call BuildHeap. So something I want to mention, this is not BuildHeap. This option 1, that is not BuildHeap. Option 2, this is BuildHeap. So I can specify this is BuildHeap. This is not BuildHeap. If we ever say BuildHeap, we are exclusively talking about this one. We are never talking about this. This is only an alternative, a bad kind of obvious way to do this, to complete this goal. So how we do BuildHeap is the first thing we do is we start with like our data in an array list or something you'll see in your constructor. We're going to copy that data into our array. There's no point in trying to start our operations before we get our data into the array. It's a complete mess. So copy the data into your backing array. Make sure you leave index 0 empty. Then you're going to start at index equal to size over 2. The reason we do size over 2 is you remember that index size is the last thing in our heap. So size over 2 is the parent of that last thing. So the reason we choose size over 2 is it's the last parent node in the heap. And then we're going to perform a down heap operation, and then we decrement our index and keep repeating. So you see we have a loop that looks kind of like this. For I equals size over 2, while I is bigger than or equal to 1, and because we want to keep going until we reach the root. There's nothing below the root, or beyond the root. We keep decrementing I, and we just call down heap at index I. Now earlier I said it doesn't matter if you make a helper method for up heap, but you should make a helper method for down heap. This is why. If you make a helper method to do your down heaps for the remove operation, this is basically the entirety of your build heap constructor. Good question that just got asked. I'll get to that later. Don't worry. So this is literally it if you write a correct down heap method for your remove method. So please write a good helper, make sure it works, and then this can be really easy. And the runtime, this is one of the few runtimes in this class where we don't actually require that you know where it comes from. If you want, you can just memorize this, that it's O of log, or that it's O of n, and not worry about where this comes from. I will talk about it towards the end of the recitation because I'm sure many people are curious, but I want to get through all of the main stuff today first. Your logic for this one, if you just want some basic intuition, is at the bottom of the tree we have a lot of data, and those down heaps have little work to do because there's not many nodes beneath them. And remember, down heap stops every time you hit a leaf node. Versus at the top of the tree, the down heaps might have to do a lot of work, but there's not a lot of nodes there to down heap. So that's kind of the trade-off, and it turns out where all of that comes up, this says goal, sorry. That's a G. I don't know how I should feel that both of your guesses were wrong. But my handwriting is not very good, I admit to this. So overall, it only becomes O of n. And I'll talk about the basic proof for that later. Also, something I want to stress is remember these down heaps are that kind of not necessarily recursive, but usually recursive structure where every time you make a swap, you keep going further down the tree. So each of these down heaps might involve multiple swaps going down, but you're down heaping at indices. This loop is going up the tree. It's a little weird, but this basic structure is what's going to get you there. I've given people plenty of time to write this down. And we're going to move on to an example of BuildHeap so you guys can see how this works. You do need to do the manual array copy. You're not allowed to use like system.arrayCopy still. That's still a forbidden method. So this is the array we're going to be starting with. I'll give people a couple seconds at the start to write it down if they want to follow along. It's just these 9 things. Remember, we have a size 10 array for it. On the homework, we ask you to create an array of size 2n plus 1, so you'd have an extra like 9 spots beyond this. But obviously, that's a lot of blank spaces that I would just have to write down to never use for the sake of this example, so I just wrote the exact amount of space I would use. So let's start with down heap. So here we have size is going to be equal to 9 at the start. So size over 2. I know this up here is probably a little hard to read, but size over 2 is 4. So this index 4 is where we're going to be starting. And we do a down heap. I should specify that this is, I believe, I'm going to be making a min heap here. No, I'm making a max heap. Yeah, I'm still making a max heap. So, index 4, its two children are 4 times 2 and 4 times 2 plus 1. So we're comparing it to 8 and 9. Now we look. Out of these two, index 9, 43, that's the bigger child. We compare that to 34. They're out of order because the parent should be larger than the child. So these two are going to get swapped. And everything else stays the same for now. Then we would look, because we just swapped with index 9. But index 9 has no children, because index 9 times 2 is larger than the size of the array. That's the check. We don't want to check if that spot is null, because that might go out of bounds. So we can check if this times 2 is larger than size, and that's an easy way to do it. Next up, we've completed our down heap at index 4. So the next thing we do is we do a down heap at index 3. Index 3 is going to compare, this is a 4, sorry, against 6 and 7. Those are its two children. Out of these two, 44 is the bigger child, so we compare 44 and 42. They're out of order, so we're going to swap them. So we're left with this data in now. So 42 is here. But again, we just did a swap, so now we look at index 6. Does index 6 have any children? No, because 6 times 2 is larger than the size of our heap. So there's no children. We're done with our down heap at index 3. Now we do a down heap at index 2. So we can compare it to indices 4 and 5. We see out of these two that this 43 is the bigger piece of data. That's larger than 29, so we're going to swap them. Everything else stays the same. And again, we just did a swap, so now we have to look at index 4. So this is still within the down heap of index 2. We look at index 4. We compare it to both of its children, because it does have children at indices 8 and 9. We see that out of index 8 and 9, 34 is the larger one, and 34 is larger than 29. So we're going to need to swap them. And remember, this is because this down heap, every time we make a swap, we need to check against its children and see if we need to keep swapping. So here we swapped from 2 to 4, and then from 4 to 9. And this is why, again, we recommend making helper methods to do this, because it's going to be really messy if you try to do it without one. Okay, now we just swapped something to index 9. So we look, index 9 does not have children, because it's past the end of our array. So now we are done with the down heap that we started. Remember, this down heap started at index 2. So now we'll do our final down heap at index 1. That compares to indices 2 and 3. But you can see that in this case, we then look at index 2 and 3. 44 is bigger than 43, but the parent of 45 is larger than 44, which is our largest child. So there's no swap we need to do. We don't need to check anything further down the tree. We stop, and since we completed our down heap at index 1, we are done with BuildHeap. There's nothing else to do. I can just copy this again without the weird circles. We are now done with our BuildHeap operation. I'm going to move up a bit, and I can actually write down what this tree looks like. I'll scroll down to it once I'm done writing, so that way people have some time to write the stuff above it. Alright, so this is what that heap looks like. If you want to take a picture of that or draw it out, hopefully you guys can probably do this conversion between them yourself, but it's very easy to check that this is a completely valid max heap that we got through doing this BuildHeap process. So this is a correct process. It works. You can try it yourself, convince yourself that following this procedure will always generate you a valid heap. So a couple more seconds, and then we will do a brief stint in priority queues, which is your mid-recitation card trick that I teased you with in the announcement. And then we'll be done with our heap talk. All right, so hopefully everyone's had time to see that by now. TAs have been very good about answering questions for me, so thank you all to all the wonderful TAs helping me out every week. They do a very good job, so I hope you guys appreciate all their hard work. Let's start talking about priority queues. And by start talking about priority queues, I mean this is kind of all I have to say, so it's not very much. Priority queues are another version of an abstract data type. So that can be a little weird because if you look in Java, priority queue is an actual implementable class, and that's just because priority queues tend to not have many different implementations. The basic idea of a priority queue is that we have some kind of priority function in our data structure, and we're always going to dequeue if we try to dequeue things, we'll dequeue the element with either maximum or minimum priority determined by this priority function. So it's called a queue, but it really doesn't have anything to do with first in, first out. This is a really huge point of confusion for people. This queue and the queue we talked about for homework 3, those aren't really related. The big thing is this priority. That's the key operator here. We have some priority function. It might just be a natural ordering. It might be how severe patients are, how severe a patient condition is in an ER queue, something like that. But we're always going to get that maximum priority or minimum priority sometimes if you think about it in reverse. Priority queues are almost always backed by heaps, 90+% of the time backed by heaps, because heaps are really good at storing which is going to be the maximum or minimum element, as we've talked about. So if we implement it with a heap, we can get all these nice log. We can get that O of n constructor with BuildHeap. We can get that log n add and log n remove. So normally priority queues are heaps, and Java's priority queue does use a min heap. It is specifically a min heap, not a max heap. If you want to have a max priority queue, you'd have to do some extra work. But it turns out that generally when people want to use heaps or priority queues for something, it's really common that they want to use min ones. We will get back to this when we get to homework 10, which is graphs. We'll talk about some applications of min priority queues, but understand the main thing is they have this priority function. They usually return the minimum or maximum element, and that's how we need to remember them by. So, another way of thinking about this, something I like to do with cards. These 3 cards are going to represent a priority queue. And again, we don't need to worry about how the things in the back work. All we need to know is that these 3 cards represent a maximum priority queue, which means if I dequeue an element, I'm always going to get the largest element in the priority queue. So if we go ahead and look, we can see that the Queen of Diamonds is the largest element in my priority queue. So I can go ahead and dequeue that element, and then I can re-enqueue it back in. Now this is a priority queue. I should always get the highest priority element, the largest element, because it's maximum. So if I dequeue again, I should get the Queen of Diamonds again, which I do. That makes a lot of sense. It's the largest priority element in there. So I can keep repeating this. I can dequeue the Queen of Diamonds, put it back in. We can see that the Queen of Diamonds is still the element I dequeue when I dequeue something. I can keep going. Dequeue it, put it back in. The Queen of Diamonds is the element I keep dequeuing for this. So that's the basic idea about how a priority queue works. You don't need to worry about the implementation or what's behind them. Just whenever you dequeue, you get the highest priority element. Now, how I actually did this, you probably guess I just have a bunch of Queen of Diamonds. Or maybe it's a little bit stranger than that. Maybe I don't have any Queen of Diamonds at all. Hopefully you guys enjoyed that. People find that memorable, which at least helps them have some association with priority queues and heaps when they talk about them. So hopefully that'll be useful. If we have time at the end of this recitation, which we hopefully will, I will do a live tutorial of that trick. And you guys can learn how to do it too, because it's actually pretty simple. There's not much to it. With that said, I'll give a little bit of extra time here if people have questions about heaps, because the next thing we're going to move on to is a very brief introduction for HashMaps before we start talking about them in detail next week. And I realize I've probably been moving a little bit fast through stuff, so I want to give people some time to ask questions about heaps before we move on, especially because heaps is your current homework. Okay, so I've waited a bit, even like after the delay, and it doesn't really seem like there's a lot of questions yet. If some lingering ones come up, I'm sure TAs will help me answer those, but otherwise we'll move on for now. I will take that as a sign that I've explained things moderately well. You guys have probably already seen a lot of this stuff before too, because this we've been talking about heaps in lecture since like almost like 2 weeks ago at this point, and it's been in the modules that you've been able to look at before then. Yes, thank you, Rena, for mentioning the visualization tool. If you want to do examples of heap-related stuff, the Viz tool is a very good resource for that. You can just try to see what things look like. You can look at how the BuildHeap works with your operations, stuff like that. Now let's talk about HashMaps. With HashMaps, we introduce a new ADT. So we talked about a lot of the things we talked about before kind of fell under the tree ADT. We talked about BSTs and heaps that were both there. So now we're going to talk about the map ADT. And the big thing with the map ADT is now instead of storing one value, we're going to be storing two values, specifically a key value pair. So the key is what we use to find the value. That's the important thing. That's how we use maps. So we might have an example of a key being the phone number mapping to a value of someone's name. So this could be like the contact list in your phone. If you start typing in someone's phone number, their name will pop up with like their information about them and stuff. It might be someone's name getting mapped to the major. So if you look on like directory.gotech.edu, you can type in someone's name and find out like what major they are, what their email is, stuff like that. That's that directory information that they're allowed to release under FERPA. How we actually implement these maps, there's a couple different ways, but the most common way that people implement maps, and the only way we're going to talk about in this class, is something called a hash map. Hash is, again, the operative word here. We're not going to talk about other implementations in this class. One of them is a tree map, which we actually almost have already talked about, but we're not going to mention it explicitly. You can look into it on your own. And another one is a linked hash map or a linked map sometimes. We're not going to talk about that in this class at all, really, but that's a decently common one that comes up in some interview questions. Speaking of interview questions, hash maps are the answer to like half of all interview questions. Like if you've looked at some like leet code problems or weird interview questions and you've been like, I have no idea how I would solve this, the answer might be that it involved a hash map somewhere in the solution. So if you hadn't seen hash maps yet, you might not have known where to start. But a lot of people ask, because this class is notorious for helping to prepare people for coding interviews, a lot of people ask like when they should feel ready. After learning hash maps, you will have learned a large amount of the basis for a lot of interview questions. So if you've been hesitant to like start looking at HackerRank problems or leet code problems, once we get through the hash map stuff, then you can definitely take some looks and you should be able to really attempt a lot of questions or at least understand their solutions. Thank you, anonymous asker. So let's talk about hash maps. Again, today is just going to be a very basic overview. We're not going to really get into the nitty-gritty details. But hash maps, as a lot of things in this class are, they're backed by an array. We've only really talked about two ways of backing things, arrays and linked stuff. Hash maps use arrays. What we're going to do is every time someone tries to put a key value pair into our hash map or do anything with a key, we're going to compute a hash value for all of these keys. The hash value kind of works like a unique, not really a unique, but it works like a fingerprint to identify the key. So all of the keys in our hash map are unique. The hash values might be the same between two different keys, but the keys itself are definitely unique. And using the hash value, that allows us to help find where the key is, or where the key could be in our hash map. It's just a much faster way than searching through to find equality. These hash values are our shortcut. These are how we know where to look. An important thing is I mentioned that the keys have to be unique in a map. The values are allowed to be duplicates. So if we look at the previous examples I mentioned on this page, it's possible that in your college, multiple people have the same major. I know, very shocking revelation that there is not one CS major in all of Georgia Tech. But we hope that at least two people don't have the exact same name. So if you consider like first, middle, last name, usually people don't have the exact same name. Likewise, people don't have the exact same phone number, but you can definitely put multiple people with the same name in your contact list. It would just be very confusing. Don't quote me on that. I've never actually tried to put multiple people with the same name in my contact list. It might not actually work. But you understand the basic idea. The name major example is a little more robust. So, the keys are unique, the values can be duplicate. How do we actually hash these things? So computing the hash is done in two steps with two different functions. I call them different functions, but only one of them is really a function. The other one's pretty straightforward. The first one's the hash function. This is how we transform objects into integers. Now, an important thing to notice is that I mentioned that hash values might be the same, and that's because, say we're using like names mapping to majors. So names are our keys. There's obviously a lot more names that exist than there are integer values that you can put in your that you can get as a hash value. And when I say integer values, I mean like Java's integer values. So there's only 2 to the 32 possible numbers we can get back, versus if you consider a name to be any string, any combination of some first, middle, and last name, you can very easily create more names than there are int values. So that's why we're not able to guarantee that hash values aren't the same. So that's where we get this property. Any two objects that are equal, if two objects are equal, their hashes have to be equal. But the opposite isn't necessarily true. If two objects have equal hashes, the objects might be equal. But not necessarily. The hash functions should be very fast to compute. We shouldn't need to do some really complicated operation every time we compute the hash. Fortunately, Java does it for us. Java has this .hashcode function, which someone asked you are allowed to use. You're not allowed to use, you should use it. If you don't use it, you will probably fail every test. This .hashcode function, every method, or every object implements this .hashcode method, which includes our keys. So if we want to transform our key into an int value, all we need to do is key.hashcode, and that's our hash function. Pretty easy. Not a lot of hard work we have to do. An important thing is that when we compute this hash, we take the hash of only the key. We don't care about the value. We don't care about like trying to hash the entire key value pair object. We're only taking the hash of the key. So a lot of people, that's a common mistake a lot of people tend to make on the homework. Only hash the key. And you can use it just key.hashcode. Next step, after we do our hash function, we need to apply our compression function. The compression function is to take our hash and fit it within this array. Sometimes we call it an array, very often we call it a table. And that's because the hash value might give us like 2,605,000. and our array is size 15. It's like, what do I do with this large number? It also could be a negative number. You can hash something and get -2. So we need to make sure it fits in our table. And how we do it is this calculation right here. We take the hash of our key, we mod it by our table length, and then we apply absolute value to the result of that. Now I will say this again, we apply absolute value to the result of this. The order of these operations is very important. Hash, mod, abs. If you do not do them in that order, things can and will go wrong. The reason for that is because if I try to take the absolute value of the smallest integer in Java, that's -2 to the 31 by the way, you will get -2 to the 31 back out. So you get this weird thing of the absolute value of a negative number is equal to a negative number. The reason for that is because the maximum value in Java is 2 to the 31 minus 1. So to try to take the absolute value of this, it takes this largest possible number in Java and basically adds 1 to it, which wraps all the way back around to a negative number. That's integer overflow. So if you do not mod by the table length first, you risk this happening, and that is going to ruin a couple very specific things. So make sure you mod first, then take the absolute value. And for this, you're allowed to just use Java's math.abs method. You don't need to implement it yourself or anything. Good question. Two objects having the same hash can be pure coincidence. There's no... if two objects have the same hash, you don't learn anything about how equal they are. If you remember from 1331, you're allowed to implement your hash code function as return 0. That is allowed. It is bad, and you shouldn't do it, but it is allowed and it is legal in Java. As a former professor would say, it is technically correct, it is not morally correct to do that. But regardless, I think people have had a lot of time to write this down. So now let's do a brief overview using this information of what adding might look like in a hash map. So, when we add, we've got a couple steps. The first step is we take the hash value of the key. And again, that is just the key. We don't want the hash of the value, we don't want the hash of the whole object, just the hash of the key. Then we compress the hash to fit in the array, and that's that compression function I mentioned earlier. Now I know when I wrote it earlier, you can write everything on one line, and you're allowed to do that in your code, just write everything like on one assignment line. You don't need to break it up into multiple steps. That's just a choice you have to make. But the point is we apply that function to get something that fits in our array. Then we go to that spot in the array and add the key value pair there. Simple as that. But what happens if the spot we calculated, where we tried to add our value, was already occupied? Because as I mentioned, multiple keys can map to the same value. Obviously, multiple different numbers, when you take a modulus, can give you the same result. So it's possible that a different key value pair has already been put at that spot in the array. If this happens, we need to resolve that collision somehow. We call this a collision if the spot is already occupied. How do we resolve that collision? That's what we're going to talk about next week. There's two main overarching strategies. There's probing methods, which is the kind you use on your homework, and there's external chaining, which is actually the kind that Java uses. We do external chaining some semesters on your homework. We alternate back and forth. This semester is linear probing. So you'd have to pick one of those two overarching strategies. Obviously on your homework we've chosen for you. And that would be how you resolve the issue with your collision. So, with that said, that's all like the required content of today. I want to talk a little bit about some things on this homework that I didn't mention earlier. Some really common errors that people run into on the Heap homework. Make sure that you leave index 0 empty always. You're never trying to add at index 0. During BuildHeap, you're not trying to copy something to index 0. You leave that spot blank, pretend like it doesn't exist. When you make sure that, remember, left child is index times 2, right child is index times 2 plus 1. Don't switch those up or something. Another really common error is, remember that when I was doing the BuildHeap examples, I was saying that you could check if an index had children by saying, okay, is index times 2 bigger than size? A lot of people will think, okay, if I want to check if that spot exists, I just check if backing array at index times 2 is null. Because if it's null, I don't have a child. If it's not null, I have a child. But the issue with that is that can throw an index out of bounds exception. So you don't want to check a spot in the array to see if you have children. You always want to check if some index is bigger than size. That is the much safer way to check that. Another really important thing is remember that our resize condition is off by 1 because of that empty spot in the array. It's no longer checking if size is equal to backing.array.length. It's now checking if size plus 1 is backing.array.length. And those are probably the most missed things on this homework. So keep those in mind. If you want to hear me say them again, you can just rewind this part of the and watch it again, because we are probably we're gonna finish very early this week. So keep those in mind when you're working on your homework. If you test your code, you should hopefully be able to catch a lot of those anyway. And now the next thing we're going to talk about is we're going to talk about why BuildHeap is O of n, where it comes from, why it's not some weird n log n function. This is not something you need to know in this class, but a lot of people find it very helpful. So this is our example heap. You've seen I've drawn it very vaguely. I have log n levels. I have one piece of data at the top of my tree, 2 pieces on the second level, all the way down. The bottom level is going to have roughly half the data in the entire heap, and the level above that's going to have 1/4 of the data in the entire heap, then 1/8, etc., etc., etc. So these are kind of the conventions I'm going to use. And now let's talk about how much work does BuildHeap do. Well, for this bottom level of the tree, the roughly half of the data I have on the bottom level, I don't do anything for BuildHeap, because BuildHeap does down heap operations starting with nodes that have children. And all of these leaf nodes on the bottom have no children whatsoever. So I do no work. Then I can go up a level. For this level right above it, I've got roughly 1/4 of the data in my entire heap. And when I call a down heap operation on this, the most amount of work that can possibly be done is a single swap with the child. I might swap with one child and then stop. I might not swap and just stop immediately. But the most I can do is one operation. Now I go up a level. Above that, I have roughly 1/8 of my data. And here I might need to do at most 2 swaps, because I might need to swap with this n/4 level, I might need to swap with this n/2 level. That's the worst case scenario. I have to do 2 total swaps. And then I can keep this sum all the way up to this top level of my tree, which has 1 data in it, and that 1 data might need to do log n swaps. So, how can I write this in a slightly better way? Well, I can write it as a summation from, let's go, I equals 1 to log n as n over 2 to the I plus 1 times I. You can see that roughly fits with what we have. It gets a little sketchier with like these first coefficients towards the end, but you can see that that is going to work out well for us. So how do I evaluate what big O this sum is? Because this is the total amount of steps my BuildHeap performs. Well, first I can notice something. I can notice that this n here is just a constant multiple to every term, so I can pull it out. Then I can notice that this sum, if I change it into an infinite sum, then I'm obviously not getting any smaller. I'm only getting bigger. And remember, with big O, we're looking, as you'll talk about in like discrete math, we're looking at bounds above it. So this less than or equal to still works for big O. If I find the big O of this right thing, it will be the same big O for the left thing. It might be better for the left thing, but in this case, it's not going to change very much. Now here I can write this as just I over 2 to the I plus 1. Now, I look at just this summation. If you remember from like calculus, you might remember that we have things like the ratio test that we can use to determine whether or not series converge. And if we apply the ratio test to this summation, we will determine that this summation converges. And what that means is that if I take this summation, I get some finite value out of it, some constant multiple. I don't care what that number is, not in the slightest. It's not important to me. Because all I know is that when I do big O notation, I'm allowed to drop constants. I'm allowed to completely ignore them and just take the other terms. So in big O notation, this is just O of n, because that is some constant. I don't care what. I think it turns out that it's 2, or roughly 2. But I don't care about it, because in big O notation, I just care it's a constant, so this is O of n. So we have that our entire build heap method is also O of n. And you can see I could have applied the same logic between these two also, that this summation, even when it goes to log n, is just a constant value that's independent of n. So we just get O of n overall. And this is where the complexity of BuildHeap comes from. Again, you don't need to know this proof for the class, but a lot of people find it very interesting. And I'll be trying to show off kind of cool math things like this as they come up. Now, that is your complexity. If the series diverged is a good question. We wouldn't be able to do this analysis. That would probably, that would imply that, so then if the series diverged, I wouldn't be able to do this trick of switching this to an infinite sum, because then this is O of infinity if it diverges, because this goes to infinity. I would have to analyze just this original bounded sum. And if that somehow got me, well, that can't be infinite because it's a sum of finite values. We're working in real math here. So I would have to do something else. But in this case, this is a convergent sum, so it makes our work easy. All right. With that said, that's all the actual content plus extra content. So the only thing I have left to show to you guys is what I promised you guys in the announcement, that since I didn't do a card trick at the end, this week's end of recitation would be a tutorial on how to do that card trick I just accomplished. So if you want to go ahead and pause and pull out a deck of cards, if you've got one close by, or just start up your imagination and hold an imaginary deck of cards in your hands, I'll give you a second, or you can just pause. All right, so how do we do this trick? So you may have noticed that during that trick I was using my Theory 11 Green Monarchs deck. And you probably were thinking that I was just doing that to show off by using a fancy deck. And I really can't blame you for that assumption, because honestly you're partially right. But there is another reason that I chose this deck in particular to use for this example. And that's because this deck has two identical jokers. So just to show you by contrast, a standard like bicycle deck, if we look at the two jokers in it, we can see that they're not completely identical. One is in black and white and one is in color. Now, you can still do the trick with non-identical jokers. I'll talk about some of the specific things later and where the issues come in and what you might want to do to account for that. But if you happen to have a deck with identical jokers in it, it makes the trick a little bit better and easier to perform. So the only cards involved in this trick are these two jokers and whatever card you want in the middle. I like to use the Queen of Diamonds. Some people use like the Ace of Spades. You can really use whatever you want. The setup of the trick is just these three cards with the Queen of Diamonds sandwiched in the middle. We're going to keep them face down. First thing you do is you show off the cards to the whatever person you're talking to or doing these tricks to, and you'll usually mention that you only have 3 cards in your hand. Now, this isn't a meaningless gesture. You're going to use this opportunity to get what's called a pinky break in card magic. Now, what I mean by a pinky break is that when I'm putting these cards up, I'm going to keep my pinky against this edge of the card, and I'm going to let these other cards fall on my pinky instead of falling on the card. So I've got my pinky like that, and then when I push the cards together, from the top, it just looks normal, but if you take a little look, you can see my pinky seems to be stuck in there, and that's because my pinky is holding a break in between these cards, and that's important. So now the top above my pinky I've got 2 cards, and then below my pinky I've got the 1. Then I start to grab the card with my other hand, and this is called transitioning to a thumb break usually, because now I'm holding it with my thumb. It's not really a necessary step, but the important thing is the first step is flipping over these top 2 cards together. And if you've got like a deck that isn't like super old, you should notice it's pretty easy to keep those 2 cards together when you flip them. They stay together pretty easily, just be sure not to like hold on the side too much or people might notice it's 2 cards. So now you show people the Queen of Diamonds. Even though it's the middle card, you're making them think it's the top card. Again, grab that double. Make sure that you don't let the cards fall back on it when you flip it over. You want to make sure that you can flip both of them back when you're done with it. Then you take the top card off and put it on the bottom. Remember, we actually started with the Joker on top and the Queen of Diamonds in the middle. So when we move the top card to the bottom, now we have the Queen of Diamonds on top. So all I need to do now is just flip over the top card just like normal. A big thing with this trick is you generally want to try to flip the card over the same way you flipped over your double lift. So you'll notice that just like before when I lifted 2 cards, you grab the cards like this and flip it over. And that's just to make it a little less obvious when you're flipping doubles versus flipping single cards. So you show them the single card, flip it back over, then now take it and put it on the bottom. So now the Queen of Diamonds is on the bottom of the pack. So now you need to show them the Queen of Diamonds again. So this is probably one of the harder parts of the trick and what requires the most practice. It can also be difficult if you have older decks. You're going to take your index finger, slide down just the top card a little bit. You can see about how far I did. If you have like a new deck, you should find that sliding is really easy. If you have an older deck, it might be a little harder. Just try to keep a relatively firm grip with your left hand so that the top card moves on its own without anything else. Then you're going to take your middle finger with your index finger on this top card and place it on the part of the card you just revealed. Then you'll take your thumb and put it on the bottom of this card. And you're going to move your entire right hand, or I guess if you're left-handed you'd be doing this reversed, up. And the point is we want to move now only this card and this card while keeping the bottom card the same. So I'm going to move this up together until the bottom card touches my left thumb, or my right thumb. Now the setup that I've created is the top and bottom cards are aligned together with the middle card sticking out. So if I repeat this process, kind of showing you what it looks like from the side, I've got my hands like that, and you're sliding that up, leaving that bottom card alone. You're sliding it up from the middle card being aligned with the bottom card to now the bottom card being aligned with the top card. And doing that smoothly can take a lot of practice, but I'm sure if you work at it, you'll be able to do it pretty consistently and easily. Having a newer deck of cards does make it easier. So again, now my setup is my top and bottom cards are aligned together, and my middle card is sticking out. Now what you can do is pinch this bottom side. You'll be grabbing 2 cards at the same time here. Pull it out. You can relax your grip a little bit with your left hand to make it a little bit easier for these 2 cards to slide out together. And then just flipping that up to get both cards here. And you'll notice I'm using my right thumb to separate the 1 card from the 2 here. That's going to make it easier to flip them down later. So I do that to show the Queen of Diamonds. Now again, I like to flip the cards over back the same way, so grabbing them both at the bottom and flipping them over. This does a couple things. First, it helps to hide the semi-suspicious movement of you flipping the card like that. Second, it makes sure that the Joker doesn't become rotated, because you'll notice my Joker was not like vertically symmetrical, so doing it this way makes sure that the Jokers stay facing the same way at the end of the trick. So that's another slight detail that helps to make the trick a little bit better. So, now, just in case you're wondering, my top card is a Joker and my middle card is a Queen of Diamonds. So when I move the top card to the bottom, all I need to do for the next step is just flip over the Queen of Diamonds again. And you can do like the side flip like we did for the first 2 cards, or you can do a single card pull and show like we did for when we were doing the bottom card. Both work. There's no significant difference between them. The main thing is you want to show that Queen of Diamonds again, move it to the bottom. So we've now shown them 4 times in a row that the Queen of Diamonds was the top card of this pack. and they're probably really confused. And a lot of spectators in real life will usually take this time to ask you, like, do you just have 3 queen of diamonds? Especially if you like pause and start talking a little bit instead of immediately moving on to the next one. So this is a good opportunity to show them that yes, you do have 3 queen of diamonds. And how you do this is actually really simple. I believe this technique is called a frustration count. But in retrospect, when you realize what's going on, it's actually kind of stupid. All you're doing is you take your right hand, grab the pack, flip it up, and show them that the bottom card is a queen of diamonds. Then you're going to flip it down into your left hand, put your thumb on the top card of the pack, slide it off, and then just show them the bottom card again, which is also the queen of diamonds. Then you can just repeat the same process and show them the queen of diamonds again, and you've just shown them the queen of diamonds 3 times. However, there is one slight alteration to this. After you do the first one, you're going to want to get a pinky break before the second card. So when I pull off the second joker, I'm not letting it fall on the other card, I'm letting it fall on my pinky. I'm holding that break there. And again, it's hard to see from above, it's hard to see from someone in front of you. You can really only see it from behind the person. So even like from the front, you can see that you can hold those cards together pretty well and not notice that I'm holding a break. Then the third queen, you can just place on top. And now you've shown them that you do, with air quotes, have 3 queen of diamonds. And then usually they'll like start laughing and be like, okay, yeah, I get what's going on. But then you throw the real kicker on them. You're going to show them that you don't have 3 queen of diamonds at all. You actually have 3 jokers. So what you do is you first flip over that double. Remember, you got that pinky break, so you have this double card. Show them the joker. Then when you flip this one down, you lose the break afterwards. And you're going to put the top card, which they think is a joker, down. But what you actually just put down was the queen of diamonds. So now you're clean. The only 2 cards in your hand that you have are jokers. So there's no real way to mess it up at this point. If you have identical jokers, you can just go and show the next card and then the next card, and that's fine, because they won't be able to notice. If you don't have identical jokers, you don't want to do this, because this is going to involve showing them the same joker twice in a row, and that can be a little suspicious. So you can do alternatively what I did during the trick, where then you flip the whole pile up and show them the bottom joker, peel that card off and put it down, and then to show them the last joker, a lot of times I like to do this little flippy thing, where they don't really get a ton of time to look at the joker, and a lot of people won't notice that it maybe isn't already a joker that you've already shown them. But however you want to show those last 2 jokers off is up to you. The important thing is to use that first one as an opportunity to put down the queen of diamonds. That's all there is to the trick. Hopefully it was mildly understandable and you guys could learn about it. There are definitely some online resources that teach it, but since I did the tutorial in Recitation, I'm not going to link those next week to keep the announcement from being shorter and not having an also section. But hopefully you guys have enjoyed Recitation. I will just wait for the live stream to catch up, and then I'll be ending it off. Thank you guys for coming. Have a great rest of your week.